maybe good morning somewhere. I'm going to talk, just moving my Zoom toolbar. Right, so my name's Tom Wickham-Jones, and I'm going to be talking about the development of the Wolfram Compiler, which is a project that a bunch of us at Wolfram Research, particularly myself and Abdul Dakak, have been working on. So, this talk, I want to cover some ideas of the Wolfram language. That's the language that we're trying to compile, the Wolfram Compiler. Some interesting ideas of embedding a compiler in an existing language. I'm going to talk about the compiler type system, some trade-offs and resolution, interesting and notable features, and some other tools and things that we put together for sort of program transformation with some automatic differentiation technology. So Wolfram language, many people might have used it embedded in Mathematica, which was, Mathematica has been around for a long time, since 1988, and it was, released as a system for doing mathematical computation. So, and it has a bunch of features for doing computer algebra and various computation types of things, trying to automate lots of parts of mathematics. So the programming language that sits underneath it has a functional programming style, and it's set up to be execution via AST, abstract syntax tree rewriting. There's a pattern matcher that works on this AST, and I'm just going to keep watching. Right, fine. Pattern matcher that works on the AST. We have function definitions via patterns and various specialized optimizations. So I'm telling you a little bit about the language just because it'll help to understand what our compiler is doing. So some details about the programming language. It has some similarities to Lisp in that it has this uniform expression structure. And the way that it works is a parser creates a Wolfram expression, a sort of tree-structured object, and then this goes into an interpreter or an evaluator that evaluates it infinitely to a fixed point. So it's typeless. That really means runtime typing, and it's not a completely pure language, so it has certain side effects. So just a quick primer about this Mathematica expression, these ASTs, is that everything in the system is represented as an AST. So we might have some sort of container that you might write like this, and so it has this sort of, head or something and components, or an arithmetic expression is like, has a head of plus and the arguments, or a graphics expression has an AST representation or some mathematical typesetting or some mathematical assertion or something expression. They all have expressions, a representation in this syntax tree structure. And the same applies to code. So code is really treated the same as data. They're kind of mixed together. And so you might have assignments, or there's a lambda function, and this is a sequence of instructions that will get executed. And this is an entire function definition. So all of these are represented in the same syntax tree mechanism. So we'll just have a quick rundown. I can introduce a variable or a symbol, give it a value, and then when I execute it, it returns the value. I can introduce a lambda function, and then when I give the lambda function an argument, it returns the value. I can use a scoping construct. I can execute a sequence of instructions, and I can make a function definition and then invoke it. So that's a lightning quick example of some programming. And another feature of the programming language is the pattern matcher. So for example, I can see a subscript, and it's A subscripted with B, and it has this full form, and the pattern matcher works at the AST level. So here I'm taking the subscript, and I'm going to generate another subscript where I've reversed the base and the subscript. And so when I apply this to the input, it's reversed the thing. And so that's a rewriting pattern matcher, and that will work for anything. And that's some of the benefits of this system are that everything is serializable. This expression, you can write it out to disk. It also makes it very easy to overload and modify and customize parts of the system. And it also means that this uniform structure means that programs work on different areas. So you don't need a special language for graphics and graph theory and algebra. The similar techniques can work in all of them. So those are the benefits, but there are some challenges that come out of this. So one big challenge is that you can make an AST out of anything, but it does mean that everything means something. So it's very easy to construct nonsense. So I could construct, this is a valid Mathematica expression, a sinus function applied to a Boolean value, and it doesn't get rejected or something. Now, actually, in mathematics, as many of you will know, nonsense is a very subjective thing, and it's context dependence. And what might be nonsense to somebody, there might be a theory about what this thing means somewhere else. I'm not saying that's the case here, but it's surprising what you can find. So, because of these challenges, it means that verification of Wolfram language programs can be hard, and efficiency can be hard. And because of these things, often the core system and what we want as performant code is often not written in the Wolfram language. It's written in some sort of internal system. But despite all of this, many very large Wolfram language applications have been written natively in the language, and the Wolfram Compiler is an example of one of them. So let's talk about compilation, Wolfram Language Compilation. So some of the reasons that we might want to do is to carry out reasoning on code. We might want to detect errors. We might want to do refactoring, select algorithms, make optimizations, transform programs. And the key thing, of course, is improving performance. We want to avoid this AST interpretation, which can be slow. We want to try and target the sort of hardware on my machines, and we might also want to target accelerators like GPUs. So in Wolfram Language Compilation, there are some specific to the language, some challenges. So the infinite evaluation semantics, the immutability semantics. We have a system of holding, or what many people might call quoting. We absolutely need to stick to the semantics of the language that we're compiling. So like for example, in arithmetic, we need to follow cross-platform compatibility, and there are various other challenges in the language. Despite all these challenges, a long time ago, a compiler was developed which worked on a subset of the language that focused very much on numerical types and numerical computations. So, and it worked by translating operations for a fixed set of types to a bytecode, and the bytecode was either interpreted or exported to C and compiled further. And this compiler was very popular with users who wanted to boost the performance of their code, and in its way it was quite successful. I spent a lot of time working on it, and the bytecode interpreter really was quite fast, actually. We squeezed everything out of it that we could. However, over the years, we started to feel that there was need for a new form of a new compiler, and we started a totally new project that we put together. Started this about 5 years ago, and we wanted to build it in our language, not in some other language, and we wanted to leverage, the latest knowledge and technology in compilers. A first version was released with Mathematica 12, April of last year, and then we've had updates, a couple of updates. Actually, this one has not quite come out yet, but I think it's going to come out pretty soon after. It's very nearly finished. It's finished as far as us compiler developers are concerned. Now, some of the operations or overview of the compiler, the idea is it converts Wolfram language code into native machine code. And part of its workflow pipeline is it uses LLVM as a backend. It makes quite a lot of use in its main usage. It makes use of the in-memory LLVM JIT compilation system, but it can also make dynamic libraries or standalone. The dynamic library is quite useful for sort of caching the results. It has static type annotations with an inferencing engine, and it provides an alternative execution model for the Wolfram language. So, just to reiterate, what we're doing is compiling an existing language. And this has some challenges, some issues. It sets expectations. People expect certain behaviors. It constrains the semantics. It also constrains the syntax. So it's kind of nice that we don't have to go and write a new parser for a new language, but it also means that we can't tailor the syntax, you know, because lots of things have already been taken up. So those are constraints. So here's the sort of standard pipeline that we follow in the compiler, is that we start with this our syntax tree, and then we do some transformations on the syntax tree, but pretty quickly we turn it into an SSA intermediate representation, and then we start working on that. We do type analysis, and then we do various transformations for optimizations or for real features like memory management or exception handling. And then we generate an executable that's integrated in our evaluator or interpreter. We can also generate LLVM or other executable output. So here's just a quick, so I've got a function here, and I'm generating an IR, but this is the basic level of SSA IR, and there's no type annotations, and I haven't said what version of plus and times this actually is. Now I'm going to do a sort of more partial thing, which is basically running type analysis. And so now I've given type markup. So I've said, you know, this is, you know, these are, you know, the input was an integer 64, so this is integer 64, and that's, you know, what's going to come out of the function at the end. We can then go and do a full sequence of transformations, so doing type analysis, and I've started to expand out and select and implement actual function calls. So it's a bit hard to see this, but I'm calling the addition has turned into a special form of addition that tracks overflow. And if there was an, you know, like an overflow happened, then that leads to a runtime error propagated by an exception. So that's the generate, you know, the IR. And then the final stage is we pass things to LLVM, and we're going to generate an executable. So in the interpreter, that's represented by this compiled code function, which basically is a sort of reference to the actual executable that we generated from LLVM, and then we can invoke this and we get the answer. We can also, for example, generate a string of LLVM IR. Typically, this is only useful for us, for developers who want to see, you know, see what's actually running. It gives some insight that's a little bit higher level than the native assembler code, though we look at that as well. Now, I'm just going to show you a quick slide to show you roughly a more higher level view of what's happening. So one of the things is we're embedding this compiler, the compiled code, so that it's accessible from our interpreter. So we have this interpreted compiled boundary. So in the interpreter, we have one uniform data type, that's Mathematica expression, and then we execute code in an interpreter or in internal code. So we then make a function call, and we've generated, we have some compiled code. And in the compiled code, there are many types that have been created by the compiler. One of the types is actually the expression type that the interpreter uses. So that's quite useful. And the execution of functions takes place by native machine instructions. And this whole thing is generated dynamically by LLVM JIT. So making a function call and the result comes back. So one key part of that is there's this sort of interface function that sits in between the interpreter and the compiled code. It's actually a compiled function, but its purpose is to unbox expression input coming from the interpreter into an argument type and then box the results coming back in. And this boxing code can be supplied dynamically to support different types and things. Another detail just of this interface is that when things are executing in compiled code, they can also call back into the interpreter to implement some feature that's that we don't have the compiled version for. So just another consequence of this way this whole thing is sort of wired up. So we have interpreter with interpreted code. We make a function call into the compiled code created by the Wolfram compiler, but that's, it's implemented in a, it's native machine code, and that itself can call external libraries. LLVM lets you link to other external libraries, and so we can call things like the CUDA runtime, or any external library, or the OMP runtime, or some library. And what's nice about this is that since this code here is created dynamically, this is giving us dynamic scripting access to external libraries. So we kind of find that all quite useful. Now, let's talk a little bit about the type system that we've developed. So type system, we looked at we spent a lot of time looking at different languages and modern languages and older languages. And one of the things we spent a lot of time was looking at Haskell. So we like Haskell and the Scala type system. And we've implemented a system that we have ad hoc polymorphism, so function overloading, different numbers of arguments, and also a parametric polymorphism. So we have type classes, and one of the benefits of type classes, then we can quantify the types, so to help selection and narrowing. We have defaults, we can set defaults for types. We have, in the ad hoc, the overloading thing, we put a lot of work into gaining ambiguity resolution, try and make that work nicely. We have dependent types and an evaluation of dependent types. One thing that we definitely do not have is there's no subtyping. So there's no, each entity is only an instance of one class, not more than one class. So just for modularity and abstraction purposes, we've developed our type framework to be independent of the compiler. And one of the goals of that is to allow it to work. Then we can work with other groups at Wolfram who are interested in type theory. There's a whole use of type theory for theorem proving. That's slightly different from sort of programming uses of types. Now, so here's just a little rundown on how the type inferencing engine works. We have our program, and then from the program, we generate a whole load of different constraints. And there's some sort of graph, they have dependencies, it's a sort of sparse graph. And then we solve the constraints. And then if we can achieve a consistent and unique solution of the constraints, then we go back and mark up the SSA variables with the types that were generated. So in terms of type constructs that we support a range of different atomic types like integer or Boolean function types. We support types that depend on types. So here I've got a handle or a pointer, but that handle needs an argument. So this is a handle to an integer 64, or we might have a handle to a function, a pointer to a function. So we also have types that depend upon terms. So here we have our numeric array. So this is a core, it's a bit like a NumPy array or such like. And this is a rectangular numeric array that contains 64-bit integers, but it has a 2 here, which means it has 2 indices. So this would be a matrix. If it was a 1, it would be a vector, and we support an arbitrary number of higher, dimension tensors. Polymorphic constructs are implemented with a type for all. So we have a variable v, and so this represents a function that takes a type and returns that same type. So it could be an identity function. The polymorphic functions can take predicates. So here I've said that the variable v is constrained to be an element of a type class number. And then we also have product types like structs or records, and sum types, which are sort of a union. And with this, we can construct a whole load of things. Now, in order to put together the Wolfram language, to support to support the Wolfram language, we need to take our compiler and write lots of functions and develop types in it in order to support the language. It's no good just having a compiler. You actually need some concrete implementations that exercise the compiler. And so we've developed a big library of functions and types for the Wolfram language. Of course, the polymorphic type system is a fantastic assistance because there's much less code to write, but you can have confidence that your code's going to do what you want. So you can give some insight. So we have some. I'm just bringing up a little sort of report that we have, and so this is a listing of all of the types. So we can see here, this is the sort of real 62, real 16. See the sort of inheritance graph of real 16. This is a listing of sort of type products. So we've got where's kind of like an interesting one, a doubly ended queue that we might see here. And then we have these abstract types. So these are ways of, these are a bit like interfaces in a way. So we can see the integers, abstract type. These are the concrete types that are elements, and we can sort of navigate through through these and see these different types. And let's return to my talk. Right. We also have a listing of the functions that we've put together. So for example, we can see here, that's kind of a boring one. Let's look at something bit XOR. So here we've got bit XOR. These are the different compiled versions that we have. So we've got bit XOR. It's set up to work with integers and with integer arrays of as well. So that's all quite useful. And then we've set things up so that if you click on these little WL, it goes and it opens up this is opening in Xcode, opens up the source code for this is the actual implementation of these functions. Let's come back to Wolfram Compiler. Right. So let's have a little look at some of the types that we've provided. I think that's quite interesting. So we need a big collection of types to compile Wolfram language. I mean, we need all the sort of core types, but we need quite a lot more. And I'm just going to talk a little bit about what we've done with the container types and how our compiler's been helpful for that. So a common, this thing called list is a general container, and we have this sort of brace syntax, which is a constructor, like a convenient constructor for lists. So lists work both for, if we have like numerical vectors and matrices, they have to be fast and efficient, and we want them to interface with like, HPC libraries like MKL or something and be nice and fast. But we also want them to work for sort of more general things, say like lists of strings. Now this works totally fine in the Wolfram interpreter. So I can make a lambda function and give it numbers, and I get back a list of numbers, and I give it a string and I get back a list of strings. In the compiler, things have to work slightly differently. So here I've taken the function, and I've given it a type annotation, integer 64. And so this, I can execute it and I get back something that looks pretty similar, but you can see here that it's made a type that's a packed array. And then here's another instance. So I've added a string type annotation. So this is a lambda function that's compiled, that takes but this now is returning a different type, a list array of strings. And this also returns string. So we've designed this, we've overloaded the list constructor to give different types for different inputs that we found useful. So the packed array type, here, we were doing integer 64 with 1, but this could be a matrix or something. It's designed to be an arbitrary dimension tensor that's compatible with numerical libraries. It's like a NumPy array, or R must have a similar thing. It's backed by a C array, a block of memory where everything's laid out, and in a way that's going to go into these fast libraries. But we also had, for things that aren't integers, we have this list array, and that's an array of anything. So it doesn't have all these constraints, but we're still able to work with it and do useful operations with it. So we have types. We also have to provide a load of, a collection of functions. So the compiled code has, lots of types. So it's not just, the interpreter has expression, but the compiled code has, even within integers, has many different types of integers. Now, there's a definite trade-off, because we want this code to be fast, but we want to maintain semantics, and we might want to provide some ways that people can start to sort of modify their code to sort of tune the difference between semantics and speed. And I'm going to give a little example of some of this by talking about arithmetic. So here I've got a 64-bit integer, and I'm adding 1 to it. So when I give 2 to the 63 minus 2, it adds 1 to it and get the answer that we might expect. But if we go 1 higher, then we've overflowed the size of 64-bit integers, and the code detects an error and gives us this warning. It throws an exception, and in the interpreter we get this sort of failure object out. Now, actually, you can set a runtime error handler which will repeat the computation in the interpreter if you just want to run your code but then fall back to something that does something different. Now, this validation is a runtime error. We can't really catch this at compile time, and it's thrown an exception. Now, with modern compiler intrinsics, it's actually, LLVM provides some very nice intrinsics that it's quite fast to catch these things. But there's still a branch, and branches can cause all sorts of optimization problems, e.g. loop optimizations. And because of this, you can turn off. So now, in the function, I've said use an unchecked block, and so that one worked fine. And this one here, no error. What's happened is it's wrapped around. So it's 2's complement arithmetic, and it's wrapped around. So you've got the wrong answer there, but it is actually going to run a little bit faster. Now, another semantic feature is the ability to sort of terminate or halt long-running calculations. So here I'm starting a calculation and it's running. It's going to take a long time. And in the Mathematica system, I can do an abort. So we can do the same thing with compiled code. So I run the calculation, and then I can abort the calculation, and it hasn't quite finished. The compiled code runs a lot faster, so I have to put a bigger limit in it. Now, this is also this check for the fact that there's some termination signal coming in. Also takes some time, and that can be disabled by setting abort handling goes to false. So for truly performant code, what one would do is one might set up an unchecked block and disable this abort handling. And that's the way to make code that's actually going to end up looking the most like C or C++ code that you might write. And our execution of these functions is actually quite competitive. Right. Now I want to show you some of our disambiguation technology. And this is a thing that's built into our type system. We put a lot of work into the type system. So the idea is this: you have overloaded functions. It's the type system inferencing that selects which function you've actually used. And the way that it works is it actually creates sets of branches of alternatives that are then pruned. And so, for example, I'm going to make a couple of function definitions. So there's one function that's the same name of function, and then one is defined for integer 64 input, and the other is designed for unsigned integer. And then when I run the compilation, it sees, oh yes, the input was an integer 64, so it's selected the function that was an integer 64. Now, I've only given two versions of this function, integer 64 and unsigned integer. So if I asked for it to compile a Boolean, there's no version, and so the type system doesn't find a definition, and you get some sort of useful error message. There's a bit more metadata in, like which function that was in and such like. Now, let's add a polymorphic definition. So this is yet another version of this function, and now I'm saying this is going to take any input, and it's going to return a string. They're going to return a string, and this is the actual string it's going to return is the literal general. So now I run this on my Boolean, and now it's picked the one that's the general. But the integer 64 one actually has two choices. It could pick this general version or the specific version, and we set things up to pick the narrowest thing. And we base this on a concept of a subsumption mechanism. So let's say we've got two choices. We've got this polymorphic function or this monomorphic function, and we choose the one that, so since this can be instantiated into this by the instantiation of substituting every instance of LM to be integer 64, that this is the one that we might choose. This is the narrowest function, or in another sense, it's the one with the most information. And that's the one that we chose. And this subsumption technology is very nicely defined, and we use this, and it makes it very, very predictive and easy to understand how the system works, how you're compiling. Now, I'm going to show another form of disambiguation. So this is something that's quite common in scripting languages. I know there's some R people here, so I'll add R here. And the problem is that in the syntax, you often get things that, it's not quite obvious what it means. You see something like this. So what is this? Is this a function? These are taken from Mathematica, but similar things, similar ambiguities apply in other languages. So here, f is a function. And here, f is a lookup table. So this is a key in a lookup table. Or here, we built this data structure library, and this is a method call. So they're all they're all different, and yet this particular thing here, they all look the same. So we taught our type system to work with these ambiguous syntaxes. So again, it creates alternative branches and then prunes them using the same technology that's used for function overloading. And so I'm not going to work on all these, but it works. And this actually has proved to be very useful, and I think this is a fairly unique feature of our compiler and our type system. So that's actually something that's quite nice. Now, slightly going to run down. I'm just running the last few things, I just want to show some of the benefits that can accrue from embedding in an existing language. So there's an outer language, and there's all sorts of nice benefits. And I'll show some of these, not least of which is it can be a fallback for missing features while we're developing things out. So here's a thing where I can use, these are just like pure Wolfram language programs, and I can create a list of type names, and then I can use those type names to create a whole set of functions. And actually, I don't know if any of you have ever worked instantiating C++ templates, but if you want to instantiate a whole load of templates over some outer product of different types, it's astonishingly complicated. You have to, the Boost has these macros that are essentially outer products, but they're very complicated. And when they go wrong, it's incredibly hard to figure it out. And yet, Wolfram language, this is a very natural and simple thing to do. So this is using the Wolfram language outside to generate programs that can be compiled. Another use of the outer system is there's lots of mathematical knowledge in the Wolfram language, and you might want to make data tables. So for example, you don't have to read all of this, but this is like a function that tests, it's a primality testing. And to use the primality testing, you might want a table of prime numbers. And that's pretty easy to generate. So what this program does is it generates a C array of this table, and it looks a number up in the C array, and if it's stored, then the thing's probably prime. Not probably, it is prime. And in fact, there's a much cleverer way of doing this, where you pack everything down to one bit and such like, which is a bit more complicated. Here's another nice real case utility that we might want to do, and that's to use some of the visualization features of the system. So Mathematica has long had nice visualization and graphics and things, and so it has a nice graph visualization. And so, what I'm doing here is I've got some code, and I want to get some view into it. I want to see the control flow graph, but I don't want to see all the individual steps. In each one of these blobs, it's like an SSA basic block. I don't want to see all the details in that. I just want to see the flow. And so this is something, we use this an awful lot when we're developing things. We can get a nice development workflow from the whole system, where we can work with interpreted code and then add some type markup and compile to faster things. Right, just going to try and run through the last few examples. It's going to talk a little bit about automatic differentiation. So again, a lot of our background at Wolfram Research, a lot of our goals are to generate a HPC, performance computing, and derivative computations are very important for lots of computations. And you can generate the derivatives by analyzing the code. And actually the SSA form works quite well. It's really a bit more suitable for multivariate problems, where it's actually generating a projection of the Jacobian. And I'm just going to show it for a univariate case, just because it's a little bit simpler. So here I've generated a series approximation of the sine function and compiled the version of it, and then I can plot that out. And actually, look, it's not a bad approximation. Now I'm going to run this into the automatic differentiator. And what this does is it returns a function that you give it a value of the independent variable, and then it returns the value of the function and the projection of the derivative in one direction. So this is a univariate function. So it's but it's good for examples. So I'm going to generate a whole load of data points and then plot them out. And so this one here, this is the sine function, because I'm going from minus pi, and here is the derivative, which, as it should, looks like a cosine function. So that's really quite a nice feature of the system. We've been developing, this is much more primitive, not worked out, GPU integration. But the essence of GPU integration, working with CUDA, is you generate PTX code, which LLVM can do that, and then you need to integrate with the CUDA Toolkit to generate host code for memory setup, launching, and such like. And so we can do all this. The CUDA Toolkit is written in, has a C interface, so we can generate a scripting access by building compiled functions, scripting access to this, and then we can write a kernel, and then we can compile that kernel dynamically into the sort of PTX language. So this is quite nice. We've gone from Wolfram language to CUDA with a sort of scripting type interface. So last two slides, just finishing up. Current directions. One of the key things is the compilation speed is still a little bit woeful. Compilation is very slow. Generated code is fast. Solution is to compile the compiler. And then we've got various things of filling out feature sets, such like enhancing tooling and adding more HPC features. So last slide, just give a quick summary. I've been showing you showed you some about the Wolfram language and our compiler and some of the ways that we've been using the compiler. And I'll just finally end up to say that we've got lots of opportunities for developers, interns, collaborations. We're developing all sorts of interesting technologies, and we're very interested in compilers are fascinating things, and there's lots of scope for working with things. And if anyone wants to get in touch, exploring jobs or internships or just chatting about them, then there's some contact info. And I think that's me actually. So thank you very much for listening. Thank you.